Okay, good afternoon all. Can you all hear me?
Yes, madam.
Okay. So, how was the quiz? It's not a difficult one, I guess, right? So it's a simple quiz. So most of you have obtained more than 50 marks. Okay, so today, okay, can you see my screen?
Yes,
madam.
So we were on chapter 3, discrete probability distributions. So far we have discussed some distributions, right? So you know now what is a random variable and how a probability distribution defined, and two types of probability distributions, discrete and continuous, and we are discussing on special distributions. So under special distributions, again discrete and continuous, so we were discussing on discrete probability distributions, right? So under discrete probability distributions, we already discussed about two distributions. First one is discrete uniform distribution, and the second one is Bernoulli distribution. So in a discrete uniform distribution, each and every outcome has the same probability. So it's a discrete uniform. That's why it's called uniform, as uniform, the same probability, uniform probability throughout the outcomes. So it's a discrete uniform distribution. And in Bernoulli distribution, there are some properties of a Bernoulli distribution. So in a Bernoulli trial, there is only two possibilities as selected as outcomes. There are only two possibilities. So we name those two probabilities as success and failure. So we denote the probability of success using simple P, right? When the probability of success is P, then the probability of failure is Q, that is equals to 1 minus P. Since there is only two outcomes, the failure should definitely 1 minus P, right? And we denoted the probability distribution using Px into 1 minus P, 1 minus X, right? That is a Bernoulli distribution. So now today we move to the next special discrete probability distribution, that is binomial distribution, right? So actually the binomial distribution is an extension of Bernoulli distribution. Why I am saying that? The properties are same, but the difference is there are n number of trials, n number of independent trials, right? So let's first learn what is a binomial experiment. A binomial experiment is a statistical experiment that has following properties. The experiment consists of n repeated trials. N repeated trials. So in Bernoulli distribution, we have only one trial, and here there are n number of repeated trials. For an example, if we toss a coin, we can obtain two outcomes, success and failures. So there is only one trial. If we take obtaining head as a success, then other one is obtaining tail is a failure. Okay, so if P is obtaining head, the probability of obtaining head, 1 minus P is the probability of failure. So it's a Bernoulli trial. So if we toss the coin n times repeatedly with repeated trials, those are called as trials. So it's a property of a binomial experiment. Each trial can result in just two possible outcomes. We call one of these outcomes as a success and the other is a failure. The probability of success denoted by P is the same in every trial, right? When we toss in the coin second time, the probability does not change. In the third trial, probability does not change. If, for an example, say probability of obtaining head is a success and the probability is half, in the second trial also, the probability of success would be half. In the third trial also, half. If it is changed, it is not a binomial experiment. The probability of success should be same in every trial to be a binomial experiment. The trials are independent. That is, the outcome on one trial does not affect the outcome on the other trial. Right? So if the second trial should be independent of the first trial, it should not be depend on the previous trials. Right? So if the trials are independent, that is also a property of a binomial experiment. So consider the following statistical experiment. You flip a coin 2 times and count the number of times the coin lands on head. This is a binomial experiment. So we flip a coin 2 times. So in that experiment, each trial consists of 2 results, 2 outcomes. The experiment consists of repeated trials. We flip coins 2 times. So here number of trials are 2. We flip the coin twice. So number of trials are 2 and each trial can result in just 2 possible outcomes, heads or tail. Only 2 outcomes. Only 2 outcomes and 2 trials. The probability of success is constant. So since it's a fair coin, we consider it as a fair coin. So the probability of success should be constant in each trial. When we toss the first time, the probability of success should be 0.5. If we toss the coin second time, also probability of success is 0.5. So it's a constant. The trials are independent. That is, getting heads on one trial does not affect the whether we get heads on the other trial. So if we obtain head in first trial, it does not affect to the result of the second trial. So the trials are independent. So now we can consider this experiment as a binomial experiment, right? So a binomial random variable is the number of successes x in n repeated trials of a binomial experiment. So now we define the binomial random variable. So binomial random variable is the number of success. We denote it as x in n repeated trials. In n repeated trials, how many number of successes is the binomial random variable of a binomial experiment. The probability distribution of a binomial variable is called a binomial distribution. So the random variable is number of success. So x can take some values. So the probability related to x value is called a binomial distribution, right? So now I think it's clear, right? So there are some examples. State whether the following examples are example for binomial experiment or not. Okay, consider the first one. Consider the experiment of tossing a coin 5 times and on each toss, observing whether the coin lands with the head or tail on its upward face. Suppose we are interested in counting the number of heads appearing over the 5 tosses. So there are 5 tosses. That means how many trials are there? There are 5 trials. right? Each trial has 2 outcomes, right? There are five repeated trials, and in each trial, it contains just two results, 2 outcomes as success or failure, in here head or tail, and the probability of success is same in each trial. In each 5 trials, the probability of success is same, and also the trials are independent, right? So X can take values from 0 to 5. There are 5 trials, okay? So this is an example of binomial experiment, okay? So this is an example of binomial experiment. So example number 2, an insurance salesperson who visits 10 randomly selected families. The outcome associated with each visit is classified as a success if the family purchases an insurance policy, and a failure if the family does not. From past experience, the salesperson knows the probability that randomly selected family will purchase an insurance policy is 0.1. So in this case, he visits 10 families, right? So 10 families, that is the 10 trials. There are 10 trials. So when he visits one house, if they purchase the insurance policy, it is a success. If they do not purchase the insurance policy, we take it as a failure, right? So from the past experience, he know that the salesperson know the probability that a randomly selected family will purchase an insurance policy is 0.1. So in this case, number of trials is 10, n equals 10, and the probability of success is 0.1. Okay, the probability of success is 0.1. So now this consists 10 number of repeated trials, and each trial can result just 2 possible outcomes, success and failure. Success, purchasing insurance policy; failure, not purchasing insurance policy. And probability of success is constant in every trial, right? Because from past experience, the salesperson knows that the probability of purchasing insurance policy is 0.1. So in each case, in each family, the probability of success is equal to 0.1. Just an assumption, right? And what about the independency of trials? So since he select a family randomly, there is no any chance to be dependent. දැන් එහා ගෙදර එක්කෙනා ගන්නවා කියලා මෙහා ගෙදර කට්ටිය ලංකාවේ නම් ගන්නවා තමයි. හැබැයි in this case we assume that he select family randomly. So one house does not know the other families purchase the insurance or not. So each trials are independent, right? So this is an example of binomial experiment, right? So in this experiment, in this experiment, we can find the probability that only one house has purchased the insurance, 2, 3, 4, 5, 6 up to 10. So X can take values from 0 to 10, right? So again, this is an example of binomial distribution. Okay. Right. Now we are going to build up the probability distribution equation. So consider a sequence of n independent Bernoulli trials. If we let the random variable x equals the number of observed success in n binomial trials, right? So there are n trials and the random variable is assigned as capital X. So the probability values x can take are 0 to n. Okay, since there are n number of trials, 0 to n possible values x can take is 0.0 to n. So if x success, sorry, this here, this should be simple x, right? Not the capital X. Correct it as a simple x in your note. So if x successes occurs, then there are n minus x failures, right? So if we consider that if there is x number of success case, then how many failures? N minus 1. N minus 1, n minus x, sorry, n minus x. If the number of successes are x, then there should be n minus x failures. Right? So if we take the random variable capital X as the number of successes in n Bernoulli trials, then x can take value 0 to n. If the probability of success is p, then the probability of failure is, we know that 1 minus p, that is equals to q. Right? Then we can write the probability sorry, of obtaining x successes and n minus x failures in any given order. There are p to the power x probability of success, and in the same case n minus x failures, that is 1 minus p into n minus x. So this is the probability of obtaining x successes and n minus x failures, right? So there is a multiplication here, because we are considering probability of obtaining x successes and n minus x failures. Okay. Then number of ways of selecting x positions for the success in n trials, we can take it as ncx, right? ncx. So we know that we can write it as factorial n over factorial x into factorial n minus x. So altogether, probability of obtaining x successes in n trials, we can multiply these two. Nx, px, 1 minus p into n minus x, where x from 0 to n. Since there are n trials, x can take values up to n from 0. Right, so this is the probability of obtaining x successes in n trials. Okay. Now, the definition of binomial experiment. A random variable x has binomial distribution, and it is referred to as a binomial random variable if and only if its probability distribution is given by p x equal x. The random variable x can take values of simple x, that is equals to nx px into 1 minus p to the power n minus x for x from 0 to n, where x is the number of successes in n independent Bernoulli trials and p is the probability of success in each trial. Right? So as you can remember, the probability of success in Bernoulli, we denote it using the p value, right? X X Bernoulli P, but here we have two parameters N and P. Number of trials is N and probability of success in each trial is P. Right? So this is the binomial distribution. So let's see this example, then it is clear to you, I guess. Okay, can you see this?
Yes, madam.
Okay, take that one. Okay, this example, a basketball player takes 4 independent free throws with the probability of 0.7 of getting a basket on each shot. Let X the number of baskets he gets. Notice that this is indeed a Bernoulli experiment with N equal 4 and P equal 7. Right? So here, a basketball player takes 4 independent free throws with probability 7. That means N equals 4 and probability of success equals 0.7. If he get the basket, it is considered as the success, and otherwise it is a failure. Okay. So each trial is here a Bernoulli experiment, and considering the all trials together, it is a binomial experiment. Right? So we can consider this tree diagram, then you will understand. Yes, use the tree diagram below to find the probability that he gets exactly 2 basket or probability of success X is equal to, right? So in this tree diagram, B is denoted as getting the basket on each shot, and M misses, right? So this is the first trial. If we consider the first trial, there is only 2 outcomes: getting a basket or miss the basket, right? So the probability of success is 0.7 and probability of failure is 0.3. So this is a Bernoulli experiment. If we consider the first trial, it is a Bernoulli experiment, right? So the player takes 4 independent free throws. This is the first trial, and this is the second trial. This is the third one, and this is the fourth trial, right? So in each trial, the probability of success does not change. It is 0.7, right? And also the trials are independent. So the whole altogether, we can consider this as a binomial experiment, right? Binomial experiment. So it is an extension of Bernoulli distribution, Bernoulli experiment with n equal 4 trials. Therefore, this is a binomial experiment, right? So we need to find the probability that he gets exactly 2 baskets. That means he get the basket on each shot twice from the out of the 4 trials. X equals 2, right? So if we consider this example, right? So here we can take this path. In this path, there is only 2 possibilities of getting basket. B is 1 and 2, right? And the other one is B, M, here B, M. Okay. So I think it's big. B, B, M, M, this one. This path. And B, M, B, M, this path. B, M, M, B, this one. M, B, B, this path. M, B, M, B. M, M, B, B. Right? So there are 6 possibilities. Right? There are 6 possibilities of obtaining only 2 baskets here. Right? So if we consider this first branch, first path, so if we denote 1 as success, then first one is success, second one is a failure, third one, second one is also a success, right? Second one is success, BB, and a failure, right? Now, if we take the Bernoulli distribution to find the answers of obtaining this particular set of outcome, we know that we can write the Bernoulli distribution as Px 1 minus P 1 minus X, right? For the first trial, probability is 0.7. X can take, if it is success, 1, and 1 minus P is 0.3, 1 minus X is 0. So it is 0.7. So it is 0.7 into, again, success, it is 0.7. If it is a failure, right? If it is a failure, P, here X is 0, 1 minus P, 1. So it becomes 0.7 into 0 and 0.3 into 1. So it is 0.3. So here 0.3 and 0.3. Right? ඔයාලට මතක ඇති බර්නෝලි එකේ මෙන්න මේක තමයි හැදුවේ. So in each case we apply the Bernoulli distribution. Right? But we can easily find this using the binomial distribution. How? So we want to find exactly get 2 baskets, right? Exactly get 2 baskets. That means probability of obtaining 2 baskets is the success, and 1 minus p n minus x, that is 4 minus 2, is the failure. So this is the probability of obtaining 2 baskets. But not only this, we have here some possible number of outcomes, right? How many? That is 4, 2. So we know that 4, 2 is factorial 4 over 4 minus 2 factorial 2. So this is equals to 6. How many outcomes are there altogether in this example? 6. See, 1, 2, 3, 4, 5, 6. Those are the possible outcomes that he gets exactly 2 baskets. So this is how binomial distribution works. This is the phenomenon under the binomial distribution. Now I think it's clear. Any question up to now? Any questions up to now? Any questions regarding the binomial experiment? Right, I guess no then, right? Let's continue. Okay, right. Consider this example. Find the probability of getting 5 heads and 7 tails in 12 flips of a balance coin. A balance coin, right? So here, again, this one is a binomial experiment. How it becomes binomial experiment? There are n trials. N is equals to find the probability of getting 5 heads and 7 tails in 12 flips of a balanced coin. There are 12 flips, right? So n is equals to 12. So flipping the coins once is considered as a trial. So obtaining head or tail can take as a success or failure, right? So there are 2 outcomes, just 2 outcomes, head and tail, obtaining head and tail. So this is since it is a balanced coin, the probability is same, half and half, and also the probability does not going to change with the trial, and also the trials are independent. So this is a binomial experiment with 12 trials. Okay, so the problem asking here is find the probability of getting 5 heads and 7 tails. So if we take x as obtaining heads, right? So x can take values from 0, 1, 2, 3 up to 12. Right? So they are asking us find the probability of getting 5 heads and 7 tails. So if we take x as a success, obtaining heads, then we have to find the probability of x equals 5. Okay. So using the binomial distribution, we can write it as 5. Sorry. N is 12. 12, 5 into the probability of success. It is, we know that it is half, right? 0.5. So 0.5 to the power x is 5 into 1 minus 0.5 to the power n minus x2 to the 2 minus 5. So find the value here. So, right, so our answer is correct. So the probability of x equals 5 equals 12, 5, 0.5, 5 and 0.5 to 7. This is 0.193. Okay. So next example. A quiz consists of 12 multiple choice questions, each of which has 5 possible responses, only one of which is correct. A student who has not studied take this quiz and independently guesses the answers to each question. That is, for each question, each response has an equal chance of being chosen. Right? Let Z denotes the number of correct answers made on the quiz by this student. So does Z follow a binomial distribution? So someone might think that this is not a binomial distribution because if we consider each trial, the question is definitely the trial. The quiz consists of 12 multiple choice questions, means there are 12 trials, each of which has 5 possible responses, only one of which is correct, right? So here there are only 12 trials and each question can be taken as a trial, right? So there are 5 responses, 5 possible responses. So someone can think this as not a binomial experiment because each trial does not have 2 outcomes, right? But the random variable is defined here as the number of correct answers, So if we consider one question, there is only 2 possible outcomes, choosing the correct answer and choosing the incorrect answer. So there is only one correct answer among the 5 answers. So the probability of there are 2 outcomes. Either he can choose the right answer or wrong answers, right? So a student who has not studied takes this quiz and independently guesses the answers to each question. So in that sentence, they are telling about the probability, right? So student has not studied. So he does not know any hint about the question. This question again, melo they done naha ya. Padan karla naha. Quiz se liwa wage do gollo. I guess no, right? Because most of you, except one student, have taken more than 50% marks, right? So my student has not studied, so he guessed the answers. That means for each question, each response has an equal chance of being chosen. 1 over 5, since there are 5 responses, he has 1 over 5 probability of choosing one answer, right? So if Z is the number of correct answers, so it is definitely a binomial distribution because for each question, the probability of success obtaining the correct answer is 1 over 5. and obtaining the wrong answers, choosing the wrong answers, probability of failures, it is 4/5, right? Is it clear? Yes. So Z follows a normal distribution. Why? There are two outcomes, successes or failures of choosing correct answer or wrong answer, two possibilities. And Z is a count of the number of successes, right? There are the trials. We are considering about the trials. So Z is a count. Each trial has the same probability, right? He has not studied, so he don't know any answers for the any questions. So each trial has the same probability, Bernoulli trials, and they are mutually independent, right? So choosing answer for one question does not depend on the choosing answer for another questions, right? So here number of trials are 12. Number of trials are 12, and probability of success on each trial is 1/5, 0.2, right? So suppose that 6 or more correct answers constitute a passing grade on the quiz. What is the probability that the student passes? So now we are asking the problem. Suppose that 6 or more correct answers constitute a passing grade. There are 12 problems. So he should obtain more than 6 answers. Now it is not only Z equals 6, Z should be greater than or equal 6. Right? So in the binomial distribution, we can take X equal X, right? Capital X equals X. Not greater than or less than sign. So how we obtain this one then? Right? How? So we have to take P X equals 6 plus P X equals 7 plus P X equals 8 plus Px equals 9 plus Px equals 10 plus Px equals 11 plus Px equals 12. Right? To find this, we need 12C6 into probability of success is 0.2 into 6 and 0.8 into 12 minus 6. Right? For this, 12C7, 0.2 into 7 and 0.8 into 12 minus 7. So likewise, we have to add up all the values, all the probability values, right? So is that clear? You can try this at home, right? So this is how we obtain binomial probabilities. Then okay. Then we can represent these binomial probabilities using a diagram as well, a bar chart, using a bar chart, right? So probability distribution of X, it is a binomial with 6 trials and P probabilities for various values of P. So we know that we can write the binomial distribution as this. Okay. So if we take x-axis as the number of successes here, x, and in the y-axis, as in, if we take the probability, right? So we can draw this graph, bar graph. How? We take the probability of x equal 1. Then this can be written as 6c1 right? 6c1 the probability of, this is the binomial graph for 6, sorry, wait a minute. Yes, this is 6-2, right? Okay. So here this is the graph for binomial distribution with 6 number of trials, and the probability of success is 0.2. So here x-axis we denote the number of successes, and here the probability values. Okay, so we can take the probability here by 6, 1. The probability of success is 0.2 to the power 1. And the probability of failure 0.85. 6 minus 1 is 5. So you can obtain this value, right? Then the probability of success, probability of success is 2 successes, obtaining 2 successes, probability is 6c2, 0.2 to the power 2, and 0.2 to the power 4, 0.8 to the power 4. So likewise, we can find these values and draw a graph. So this is called the diagrammatic representation of the binomial distribution. We can draw a bar graph to denote the, or to represent the binomial distribution. So this is binomial distribution with 6 trials and 0.2 probabilities, right? So using the same way, we can draw the binomial probability of binomial distribution with again 6 trials, but this time the probability of success is 0.8. In earlier case, probability of success is 0.2. In this case, probability of success is 0.8. Right? So in here, again, we can find what happens when number of success equals 1. What is the probability when number of success equals 1? using 6C1. And now the probability of success 0.8 to the power 1, 0.2 to the power 5. Right? So that is this value. And next one, 6 obtaining 2 success, 6C2, 0.8 to the power 2 and 0.2 to the power 4. That is this value. Right? So now, when comparing these two diagramic representations, these two bar graphs, you can see a similarity between these, right? So here, probability of obtaining 1 success is 0.262, and here probability of obtaining 1, 2, 3, 4, 5, 6. This should not, this is not 7, I guess. 1, 2, 3, 4, 5, 6, 7. It should be 0. There is some mistake, I guess, here. Let me check. Wait 2 minutes. Yes, the calculations are wrong actually, right? Here the calculations are wrong. So, here x values should be 0, 1, 2, 3, 4, 5, and 6. Okay. Here also 0, 1, 2, because there cannot be 7 here. Only 6 trials. Therefore, 0, 1, 2, 3, 4, 5, 6. The probability values are also not correct here, right? So I will upload the correct one in today evening. So you can download it. So, but just for the moment, let's continue this, right? The probability values are not correct, but if we consider what I'm going to tell you here is to point out the probability here, the probability value of obtaining 0 successes in the binomial distribution 6, 0.2 is same as probability of obtaining 6 number of successes in the binomial distribution 6, 0.8. So these two are same. And probability of obtaining just one success in the binomial distribution 6, 0.2 is same as obtaining 5 successes in the probability distribution binomial 6, 8. So there is a property of symmetric. Property of symmetric, right? So here we can notice that the probability of obtaining 0 success in a binomial distribution of 6, 0.2 is same as probability of success equals 6 of a binomial distribution 6, 0.8. Right? So likewise, probability of obtaining one success of the binomial distribution 6, 0.2 is same as probability of obtaining 5 success of a binomial distribution 6, 0.8. Right? So as a whole, this concept can be logged into this simple property, that is, here it should be capital X, right? Here also capital X, make it as capital X. Probability of X equals the success is X in the binomial distribution n, P is same as the probability of capital X equals n minus X in the binomial distribution n, 1 minus P. Right? So in this case, X is 0. So here, n minus X is 6 minus 0, 6. And here the binomial distribution 6, 0.2. But in place of 6, 0.2, we put here n 1 minus P. 1 minus 0.2, it is 0.8. Right? That is the thing I wanted to point out using this diagrammic representation. Right? So this is for equal case. And also we can use the less than or greater than sign as well. Inequalities. So here probability of x less than or equals to a given value x in a binomial distribution n comma p is same as probability of capital X greater than or equal n minus 6 now. N minus 6 trials, number of trials minus the number of successes, but not in binomial np here, binomial n 1 minus p. Okay, so this is called the symmetric property, right? Okay. So we can use this symmetric property to find the probability values, right? Let's discuss an example later. Okay. Now I think the idea I wanted to illustrate is clear, okay? Right. Then, considering the binomial probability equation, it is clear that it is very difficult to calculate by hands, right? It is very difficult to calculate by hands. So, using a computer programs, a binomial probability tables has been developed using the computer softwares, right? So in actual practice, binomial probabilities are rarely calculated directly. They have been tabulated extensively for various values of n and p. So they have tabulated the binomial probability values for various n and p. And there are computer softwares that gives binomial probability and corresponding cumulative probability. But it is in the binomial distribution, we are calculating the probability of success equals to a given number x. But in the binomial probability tables, they are illustrated the cumulative probabilities. Cumulative probability, that is the probability of x less than or equal to a given number of successes. So that is the summation from k goes from 0 to x, the binomial distribution, right? Okay. So those are the binomial tables, okay? Consider obtaining x that is less than or equal r for various values of n and p. Okay, consider this extract of the table. So this is an extract for binomial 7, 0.2. N is 7. So earlier they have said that they have been tabulated extensively for various values of n and p. So this is an extract for binomial distribution where number of trial is 7 and probability of success is 0.2, right? So this is the extract. So here, when the number of success is 0, number of success is 0, the probability is 0.2097. It is obtained using the equation 7C0 and probability of success is 0.2 to the power, sorry. Seven C0, probability of success is 0.2 to the power 0 and 1 minus P 8 to the power 7. So this is equals to 0.2097. And next value is R equal 1. Right? So here it is the probability of X less than or equal 1. That means here we should add the probability X equals 1 and probability of X equals 0. Cumulative probability. Right? So when R is 2 means the table gives us probability of X equal 2 plus the probability of X equals 1 plus probability of X equals 0. Right? So the cumulative probabilities are given. So when it comes here, probability of X equals 7 plus probability of X equals 6. Likewise, up to probability of X equals 0. All the values are added up. So definitely it should be 1. Right? So this is how the probability distribution for binomial distributions are formed in tabulated forms. මේ විදිහට තමයි අපි tables වලට tables create කරලා තියෙන්නේ. එතකොට අපි tables කියවද්දී හොඳට මතක තියාගන්න ඕනේ අපි equation එකෙන් හදන්නේ හැම වෙලේම probability එක මොකක් හරි value එකකට සමාන වෙන probability එකක්. හැබැයි tables වලින් බලනකොට අපිට ඒගොල්ලෝ දෙන්නේ cumulative probability එක. හරිද? Cumulative probability එක. That means number of success is less than or equals to the given value. The cumulative probability. Okay. Okay, let's consider these examples. So we have to find probability of X equals 3. Right? So if we find this without using the probability table, tabulated form, we can just find there are 7 trials, 7C3. The probability of success is 0.2 to the power 3 and 0.8 to the power 7 minus 3, it is 4. Right? But we can easily calculate this using, we know that probability of obtaining 3 or less than 3 value can be obtained through this table, through this entry. And if we subtract the value, probability value, that is less than or equals to 2, so then we can obtain the probability that exact success, number of success is equals to 3. Right? Because we know that here for this one, we have added up probability of X equals 3. Sorry, I write it. x equals 3 plus probability of x equals 2 plus, oops, wait. So we want to find the probability of x equals 3. So here we know that this is probability of x equal 3 plus probability of x equals 2 plus probability of x equals 1 plus probability of x equals 0, right? So here probability of x is less than or equal to 2 means its probability of x equals 2 plus probability of x equals 1 plus probability of x equals 0, right? So if we subtract probability of x less than or equal to 2 from the probability of x less than or equal to 3, now we know that these are cancels out. So the remaining is probability of x equals 3. Since we are here in the table, we have the cumulative value, right? Just a small concept here. So according to that, we can write probability of x number of success exactly equals to 3 using this one, and the table values are 0.9667 minus 0.8520. So it is very easy rather than calculating the probability by hand, right? So the next one, probability of x greater than 4, 1 and less than or equals to 4. Right? That means we need the probability values px equal 2 plus px equal 3 and px equal 4. If we use the binomial expression here, so the calculation is little bit difficult and it takes time. But here using this cumulative probability table, we can just write this as probability of x less than or equals to 4 minus probability of x less than or equal to 1. So in probability of x less than or equal 4, there includes probability equals 4, probability equals 3, probability equals 2, 0 and 1. 1 and 0, right? When probability of x less than or equal 1, it includes the values of probability of x equals 1 and 0. So if we take the subtraction, then we only get the probability of x equal 2, x equal 3 and x equal 4. So here the probability value is 0.9953 minus probability of x less than or equal 1. The value is 0.5767. So it is 0.419. up to 3 decimal places. So next we have to find probability of a number of success greater than 1. Right? Greater than 1 means probability of success equals to 2, 3, 4, 5, 6 and 7 altogether. So rather than using the expression, we can easily calculate the values, right? So if we take 1 minus probability of x that is less than 1, it consists all the probability values we want. So here 1 is probability, cumulative probability of obtaining number of success that equals to 7 or less than 7. It contains the probability of success equals 7, 6, 5, 4, 3, 2 and 1. 3, 2, 1 and 0. Right? If we subtract the probabilities that is less than or equals to 1 means probability equals 1 and probability equals 0. Then we can obtain this probability greater than 1. Probability of success greater than 1. So it is 1 minus 0.5767. The answer is 0.423 up to 3 decimal places. Is that clear? Any problem? Any problem up to now? Right. So these are the cumulative binomial probabilities built by the computer softwares. I'll explain how we are going to read this, right? Okay. Is there any connection issue? Can you hear me clearly?
Yes, madam, we can hear clear.
Yeah.
Yes, madam.
Okay. So here in cumulative binomial probability tables, in x-axis, in this axis, the probability values are given. Probability of success values are given. See? 0.05, 0.1, 0.15, 0.2, 0.25, 3, 3, 5, 4, up to 0.5. The probability of success is given there. And n is given in y-axis. Not only n, but the r values. අපි සාමාන්‍ය use කරන්නේ x කියලා. නමුත් මෙතන cumulative වෙන නිසා තමයි අපි r කියලා කියන්නේ. r කියන්නේ x කියන්නේ number of successes ම තමයි. Right? හැබැයි අපි අර x equals x කියලා අපි බොහෝ විට ගන්නෙ cumulative නෙවෙයිනේ. expression එකේදී මෙතනදී cumulative අපි table එකට විශේෂයෙන් r පාවිච්චි කරලා තියෙනවා. Right? Confuse වෙන්න එපා notations නිසා. Right? So, if we want to look at the probability, the cumulative probability, suppose for an example, we consider the binomial distribution. Let's consider N5 and probability 0.2. Right? We want the probability of X less than or equals to 3. We want to find this for an example, right? So let's see how to find this, right? So first, go through the number of trials n. Here n is 5. That means in this row, here n equals 5. Okay, then the probability value is 0.2. In this row, the probability value of 0.2 means here. Right? So we have to consider this cell. N equals 5 and probability equals 0.2. And we want the probability, the cumulative probability. That means we want number of successes out of 5 trials is less than or equals to 3. So here the R, next consider this R values. So number of success, the probability when number of success equals to 0, probability of success less than or equal 1, likewise for 3. So it is this one. 0.9933. Okay. Okay, let's see another example. Okay, let's say n equals 4 and 4, 0.4. If we want to find again the same probability of successes, probability of number of success that is less than or equal to 3. So we have to go for n equals 4 and the probability 0.4. That means this cell, then number of success less than or equals to 3. This value. It is 0.9744. So if we want to find probability of X exactly equals 3, then we can find it using probability X less than or equals to 3. It contains the probability X equals 3, 2, 1 and 0. So we can omit the probabilities X less than or equal to 2. It contains probability of X equal 2, 0, 2, 1, and 0. So we can obtain probability of x equals 3. So probability less than or equals to 3 is 0.9744 minus probability less than or equal to 2, that is 0.8208. Here you can find the value. So without using the expression, it is easy to use the given cumulative binomial probability tables. I think it's clear now, right? Any problem? Okay. So this is for n up to 8. And here n equal 9, 10, 15, 20 are given, right? Those are the cumulative binomial probability tables. Okay. Okay, can you try this example now? Okay, I'll give you just 5 minutes. Try this and send me your answers. Okay, most of your answers are correct. So I'll just write the answers here. So probability of x less than or equal 4, you can just go through the table and find the answer. It is 0.9976, right? For three decimal places, it's 0.998. Okay. Three decimal places. Okay. And x equals 2, probability of x equals 2, number of success. Probability of number of success equals 2 is, we can find it using x less than or equal to 2 minus probability of x less than or equal to 1. So it is 0.8369 minus 0.5282. So up to 3 decimal places, if we write it up to 3 decimal places, it is 0.309. The exact value is 0.3087. Then x less than 3. So it is same as probability of x less than or equals to 2. Less than 3 means without 3, 0, 1 and 2. So that is same as probability of x less than or equals to 2. So the value is 0.8369. Up to 3 decimal places, 0.837. And x is greater than 1. So we can find it easily if we subtract the probability of x less than or equal 1 from 1. It is 1 minus 0.5282. So up to 3 decimal places, it is 0.472. And the last one, probability of x greater than or equals to 3. So it is 1 minus probability of x less than 3. So it is 1 minus probability of x less than or equals to 2. Right? So it is 1 minus 0.8369. Up to 3 decimal places, the value is 163. Okay. Right. Next example. Let the random variable x be such that x is a binomial 8, 0.6. Use the extract of the cumulative binomial table for x be 8, 0.4 to find the given probability values, right? So here we have to find the binomial table for number of trials 8 and probability of success 0.6, right? But we know in these probability cumulative binomial probabilities, we are given only up to probability of success 0.5. Right? Here also, see, only up to 0.5. Okay, but we can find the probabilities using the property of symmetry we discussed earlier here. See, property of symmetry. The cumulative binomial probability is a symmetric probability distribution. As I said earlier, so it is clear when we look at the diagrammic representation as well. So we can use that symmetric probability property to find the probabilities where the probability of success is greater than 0.5. Right? Okay, let's consider these examples. Let the random variable x be such that x binomial 8 0.6. Right? Now it is the number of success is greater than 0.5. Okay. So now we want to find probability of x greater than or equals to 3. Okay. So okay, first I write the symmetric property relationship we built up earlier. We can write probability x less than x in a binomial distribution, probability of, number of trials n and probability of success p is same as probability of x greater than or equal, now it is not x, n minus x. Number of trials minus number of success, but not in the same binomial NP. Now the binomial is also changing. N is same, number of trials is same, but the probability of success should be changed into probability of failure here, 1 minus p. Right? Now we can find here probability x3 in the binomial distribution 8, 0.6. So this is equals to probability of x less than or equal n minus x. Now n is 8, 8 minus 3. It is 5. But the binomial is also changing. Now 8, in place of probability of success, we have to put probability of failure. It is 0.4. So if we can't find the probability table for 0.6 probability of success, but we can find this one, 0.4, right? So what is the value here? In binomial table, we have to look at 8 number of trials, and the probability of success is 0.4, and number of success, that is less than or equals to 5. Right? So what is the probability value corresponding to that? It is 0.9502. Is that okay? Clear? Okay, I guess yes, right? Okay, do you have lectures at 3:30, isn't it? You have the lectures, I guess, right? Okay. So I'll finish it now. So try the second part B and part C as well, using the symmetric property to find the given probabilities. Okay. Any questions up to now? Any questions? Okay, so I guess no. So try these two remaining parts, part B and part C, and also go through the next example as well and try to find the probability values. Okay, yes, we can rearrange the quiz for those who did not participate it for a valid reason. So yes. So I think you don't know each other, right? Okay. Send me WhatsApp message those who haven't participated for the quiz for a valid reason, with the reason before today 8 p.m. For those who are sending me the message, I'll arrange and also mention a possible date and time you can participate it, right? I'll again rearrange the quiz for those who did not participate for the quiz. So before today 8 p.m. Message me a possible time and date with the reason, right? With the reason why you could not participate to the quiz, right? So any questions? So I guess no. So let's meet again on Wednesday. Okay. Thank you.
Thank you,
Thank you,
madam.
madam.
Thank you, 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 madam.
You are welcome.